evaluate the integral from 2 to infinity of x minus 8 divided by x cubed plus 4x. So this one is pretty straightforward. It's going to be improper because of this upper limit being infinite. What we do to deal with that is we allow some variable to approach infinity. But also, though, we should worry about the denominator. Sometimes the denominator causes issues as well. And so if there was some place where that denominator is equal to 0 on our interval from 2 to infinity, then we'd have to worry even more. And so just to double check, factor x cubed plus 4x. Find out where it's 0 at. Factor out the x, and you'll be left with x squared plus 4, and it turns out that it's only 0 when x is 0. This x squared plus 4 is an irreducible quadratic. Plus or minus 2i technically are the roots there, imaginary roots. So our interval is from 2 to infinity, and so we're good. The fact that the function is undefined at 0, then you're okay. So we're going to introduce this limit, t, as t approaches infinity. We're going to be able to evaluate this integral and then also finish it up by evaluating the limit. So let's go to the next slide. How do we evaluate the integral? How do we perform the integration? Well, we have to recognize it as partial fractions. Okay, to start partial fractions, we got to make sure that the degree of the denominator is more than the degree of the numerator, and it is. And when that's the case, then it's our job to factor the denominator. We've done that. But then we have to recognize which of the three types of terms that we have. And what we end up with as the three types of terms are a linear term that's to the first power, a linear term that's to a higher power, or an irreducible quadratic term. Now technically we could have irreducible quadratics that are to higher powers, but let's just say we're going to end with this third option here. So our denominator of x times x squared plus 4, that quantity, represents a linear term, the x, and then an irreducible quadratic term, the x squared plus 4. Knowing that will tell us how to decompose the integrand. The linear term would be decomposed by getting some constant over that linear term. And the irreducible quadratic then would decompose by getting some linear bx plus c over that irreducible quadratic. And it's our job to chase down what the a, the b, and the c are. And we'll do that on the next slide. So to do this, we have to use algebra. Okay, we have to act like what we're doing is putting together the fractions here. And so the a would get multiplied by x squared plus 4, the b with x plus c would get multiplied by x to give us our original numerator of x minus 8. Okay, great. So now we have to chase down what the a and the b and the c are. And so if we can choose x values that would make the denominator 0, then that would be great. The only x value that you can choose, though, to make the denominator 0 is by choosing x equals 0. So let's start with that. What happens when x equals 0? This is true for all x. What happens when x is 0? Well, when x is 0, then the entire term bx plus c times x will be zeroed out. You don't have to worry about it at all. And so we're left with 0 minus 8 on the left-hand side and a 4a on the right-hand side. So negative 8 is 4a, telling us exactly that a is negative 2. Great. So we're able to get that directly. Now what we should do is choose other values of x, just that are convenient to plug in, like x equals 1. If you plug in x equals 1, we'll have 1 minus 8. And then we'll have, that'll give us a 7. The 1 squared plus the 4 gives us 5 times a. Then we just basically have b plus c after that. You have to figure out what this is. Now this won't be able to directly find b or c, but we do know that a is negative 2. We can plug that in, giving us a negative 10 there. When we add when we add 10 to both sides, it cancels it out and it tells us the value of b plus c. We don't know b or c, but we do know that they must add up to 3. And so we can use this as an elimination with the next equation we'll get, or as a substitution. Let's go with substitution and use the fact that c is 3 minus b. Pick another convenient value of x, let's say x equals 2, and plug it in. Back to the original equation, 2 minus 8 now on the left-hand side. 2 squared plus 4 will be the coefficient on a, that's 8a. And then 2b plus c will need to be doubled. Distributing the 2 across, we get 4b plus 2c. Plugging in the fact that we know that a is negative 2, we end up with negative 6 is equal to negative 16 plus 4b plus 2c. Add the 16 over, we end up with 10. It's 4b plus 2c. And because we know the fact that c is 3 minus b, we can now plug that in. We're just solving by substitution. Now we'll be able to find exactly what b is. Distribute the 2 across here, and we get 6 minus 2b. The 4b and the 2b combine to give you 2b, and then we can ship the 6 over by subtracting it, and 4 should be equal to 2b, or the b is 2. And then knowing that b is 2, that can tell us what c is, because c must be 3 minus b, so c is 1. We have all of our constants now. We have the a, we have the b, and we have the c. Let's go put it together and see if we could finish out this integration. B, a, b, and c, and we can plug them in. Now, when we have an irreducible quadratic as our denominator term, and when it's in the form of x squared plus a squared, then what we can do is break our fraction bx plus c when there is an actual non-zero b and c. We break that into 2. We have it as 2x over that x squared plus 4 and 1 over that x squared plus 4. Reason being is that it'll be advantageous for us to attack this integral with a u substitution, and the other integral is actually in the format that's ready to be an arctan. And so the first integral will just be minus 2 log x. The second integral here will use u substitution, and we have exactly the derivative of the denominator in the numerator. X squared plus 4, its derivative is 2x dx, and so we'd be looking at 1 over u du. So we get the natural log of u, technically in absolute values there. So we have minus 2, the natural log here. We got that guy. Now we know what this guy is, the natural log of the denominator. Our only mystery then would be how we integrate the third guy, and there's a form for that. If you have x squared plus a squared, 1 over that you're integrating, it's 1 over a, the arctan of x over a. And you can work that out. It's just a substitution. And so we'd have 1 over 2, the arctan of x over 2. Okay. Great. So now we put the t's in, and we put the 2's in. Remember that, we're still performing a limit later. To simplify this, though, what we can do is x squared plus 4 is always going to be positive, so we can drop this absolute value bar. And then this 2 here that is in front actually has a negative 2. Let's leave it as negative and bring the 2 up as the exponent, and then the absolute value then will always be positive after squaring it. And so then our goal is to make it as simple as possible before we go plug in. And so we're going to make the log of a minus the log of b basically be equal to the log of their division, just to make our life easier. Okay. And we can even go further with this by saying, well, I have two terms in the numerator, one term in the denominator, so I can divide and have x squared over x squared, which is 1, and then 4 over x squared. So here's what I want to plug into. The t and the 2 are best to be plugged into this. Let's go to the next slide and do that. Plugging the t in place of x, plugging the 2 in place of x. Let's work on simplifying. Before we take the limit, let's work on simplifying this right-hand side here. 4 over 2 squared, that's 4 over 4. So that's 1. And 1 plus 1 is 2. So this is basically just a 2, natural log of 2. Okay. And then we have the arctan of 1. Remember what arctan does. It asks the tangent in reverse. What angle do you plug into tangent and have it spit out a 1? Well, that's pi over 4. The sine and cosine are exactly the same. So you have the natural log of 2 and pi over 4 as the arctan of 1. So let's call it the natural log of 2 and pi over 8. And it doesn't need to be involved in the limit. We can actually pull that out and focus our limit only to be on the part that has the t's on it. And now on the next slide, we'll attack that limit. Our integration is now over, and now let's perform the limit. But think about it though, the way we have it set up nicely, we can know automatically that 4 over t squared goes to 0 as t gets big. A large number that's squared, when it's underneath a constant, goes to 0. And then our only mystery is what happens to the arctan. And to know that, what we have to do is to plug into the arctan function. But with that part going to 0, and the fact that the natural log of 1 is 0, all of our attention then can be put on what's going on with arctan, and we'll be done. Well, you have to know the graph of arctan really to know what happens as t gets big, and it being the inverse of tangent, switching the x's and y's, what we end up with is that it approaches pi over 2 as x gets big, and negative pi over 2 as x gets small. And so there we have it. We are ready now to finish this off that this guy is pi over 2, and log of 1 is 0. So we have a pi over 2 and a half. That's a pi over 4. And we're done with the limit. Let's just simplify. We have pi over 4 minus what we got from the lower limit. And the only thing left to do is to combine these guys together. Pi over 4 minus pi over 8 is a pi over 8. So our final answer then is pi over 8 minus the natural log of 2. It actually converged, and that's what it converges to.